Okay, welcome back to Kerbal Space Program 1 with a fairly modified game where I'm doing my work in some automation, some autopilot work, and some software engineering ideas. So, yeah. Am I not getting audio from KSP? Let me check this. Bink, bink, bink. Hmm. Okay, it's not clear to me whether I'm actually going to be getting audio from KSP or if it's just real quiet. So, here we are. It's been a while. So, I had this save up and running where I was automating everything, and I was able to go rescue Kerbals, and I was able to go set up satellites and rendezvous and all of that. And I took a look at the code I was writing, and some of the bits were, from a software engineering standpoint, getting irritating. They were getting cumbersome, they were getting boilerplatey. So I sat back and reworked a few things, changed some philosophies. I have returned to the original plan, which was to have packages that I import. And when I import the package, it does not touch the global namespace. So there's that. I retained the idea of not requiring an explicit export from the packages. And without touching global namespace and requiring an export, this means that my import has control over the package objects themselves. So now the model is, when you import a package, if it doesn't exist, the import mechanism creates a lexicon and then runs the package file and tells the package file, please add your stuff to this lexicon. So now, instead of having the package file create some things and export it, now it just says add this to the list, add that to the list, add the other to the list. And that's not too bad. It means that declaring a exported function means you have to at some point do an add, lexicon : add name thing. And the way I normally do it is that the thing is the actual function body. So I get a whole bunch of function bodies I create that are unnamed delegates, and I add them to the map under a name, and now I can call map : name whatever. Works out really well. Actually, let's turn the code on. So what you can see on the screen now is the actual import function. The std file has grown a little bit. I've added a few things to it. For instance, we now have at the bottom, we've got some delegates, a delegate that does nothing, and a delegate called always that returns true, and a delegate called 0 that returns 0. We have a function eval where if it's passed something, if it's a delegate, it'll evaluate the delegate and return it. So here's import. So pkg is my lexicon, which has all of the packages in it. And you say import package, it says, oh, if it's in there, we'll return it. Otherwise, we create a lexicon and we add it to the list. So it's there, it's empty, but it's there. This helps with circular dependencies, because if I import you and you import somebody else and they import them again, somebody is going to import something that's importing them. So you chase around through the circle of dependencies, and when you do that last one, he'll get a lexicon. It'll be empty, but he'll get it. Okay, so we add the empty lexicon to the package list, and we go find the file. And if we find the file, we run the file, we pass the lexicon to the file as its first parameter, and we return it. Otherwise, we're going to say import, missing whatever. So Another change is the STD itself is no longer a package. There is no package STD. If something is important enough to be an STD, it's important enough to be in the global namespace. Full stop. So this is my standard extensions to the language. And I'm going to be keeping the names fairly brief because at some point we'll be trying to cram this all down into tiny processors. For now, I am just using basically KOS processors on every core with 100 kilobytes of storage. So yeah, the other thing I'm doing is I am not copying my source files to the vessel. The only thing on the vessel is going to be the non-volatile storage. So we run from the archive. For things to work, you have to have a connection to the archive, otherwise things are not going to work, which means that if we turn the connection manager on to that scale, we have to be very careful to keep our radios active. So what does a package look like? You can see I've got a whole bunch of packages here that have been created. At some point I will have to go over them. Let's pick one just to see what a package looks like for now. VSViva has been around a while. It's simple. So here's what it looks like now. We start off every source file with LAZYGLOBAL off because I do not want anybody to be able to say set X and have KOS say, oh, I don't have an X. Let's create a global called X. Because if you make a typo, it'll just create something with that name. Boom. This goes along with the fact that we've upgraded to KOS 1.4, which now warns us if we create a local that overloads the name of a built-in. So if you're using a built-in called foo, and you create a local called foo, and you try to use foo again, what are you going to get? Oh, whatever you get is going to be wrong. So it now warns us. And this raised the note that, hey, R, V, and Q, single letters, are built-ins. They're not functions. They're not variables. They are literals. So for instance, R of 3 numbers is a direction, and V of 3 numbers is a vector. Q, I'm assuming, is a quaternion, but I haven't actually tried that out yet, so that should be another way of doing it. I've messed around with quaternions a bit in the past. And I checked KOS. You can set a direction from a quaternion. You can specify a quaternion representation of the direction, but I don't see any way of getting the quaternion back out. So for instance, I couldn't store quaternions in directions, then later say, well, I'm going to pull the quaternion out of the direction to do some math with it. Instead, what you do is you do math with the directions in similar ways. Direction math and quaternion math are not the same. So direction times vector rotates the vector, whereas to do it with quaternion, you say quaternion times vector times the conjugate of the quaternion. So it's actually simpler. So as much as I would like to mess with quaternions, because quaternions are cool, I think directions are easier. Not that I do it. I am guilty of not using directions to rotate my vectors in the coordinate spaces or change bases. Anyway, so let's go off. We get called. Our parameter is a lexicon, and I'm going to call it the name of the module. I could call this underbar. We're perfectly well. But if I call it the module name, elsewhere they say local VSViva is import of VSViva. And here I say parameter VSViva is lex. Now I can say VSViva add v, and everybody will call this by saying VSViva:v. If I've got several functions here, I could call between them using that same thing. VSViva only has the one function, so it's not a good example. Let's take a look at the maneuver package. So this was derived from Kevin GC. Cheers, Kevin. His maneuver package. I have deviated from it radically. His original code is still here, sort of. I mean, well, maneuver time is still here, but this whole calculation of the ISP that he does is now a calculation of VE, which I have taken out here. But the example I wanted to show was that if I call this MNV, I'm not only providing functions MNV colon whatever, but I can call them that way here. So this is how I call V sub E, which is my estimate the current aggregate exhaust velocity for all of my engines. And I use the formula here that works even if your engines are not the same. So you have engines with differing available thrust and differing ISP. This formula handles computation of the correct exhaust velocity. Also, subnote for anybody looking at his code or any other code that combines this, if you are changing ISP into exhaust velocity or using ISP in a context where you're multiplying it by G, the G factor there is not the current gravitation. Okay? The performance of an engine doesn't change based on the gravity constant of the area it's in. This is a unit conversion, and it's equal to 9.81 meters per second. And that converts your force divided by your whatever. It converts your ISP into a exhaust velocity. Or alternately, you take the exhaust velocity of an engine, you divide it by G to get the ISP. So if you have code that's doing this and you are using the mass of the planet and your current radius to derive gravity here and using gravity here, that's not going to be right. You would need to use the radius of the planet and the mass of the planet, or the planet's mu, or whatever. And at that point, if you're on the wrong planet, you're doing the wrong thing. So it only works for Kerbal, and the only calculation that makes sense is the one that happens to come up with this constant G0, which is available in the constant pool. So, end of side note. So maneuver, we've gone over maneuver in the past. We've got compute maneuver time. We've got compute our exhaust velocities. We've got execute a node. This is Kevin's layout. You call exec and it does all the work and then returns. So you end up blocking inside exec for a while so you don't return until you're done. I have a framework where I call something and I expect it to change the state of the system. Look at our current sensors, apply the math, do the control logic, and set the actuators for now. And I expect that to be called periodically. So I need a maneuver step that does it. It's a little more complicated because I now need to handle the fact that I'm going to do, you go down through exec and you get here and somebody says, wait. Well, instead of waiting, this is going to be a return. And then we get called back. We see, we're not there yet, not there yet, not there yet. And eventually we go on. So step has to handle all of that. I believe this may be something I did since the last time I streamed. But anyway, it's basically the same thing. We set our steering to basically be along the burn vector, and we figure out what our wait time is, and we wait until it's time. So if wait time is greater than 60, so if we've got more than a minute, we're going to lock our throttle and return. And we do a warp 2. We've got code up here that says if we are in time warp, we're just going to return. So if you manually turn on time warp, your maneuver nodes won't work. Let the maneuver node do the warp 2. So when the warp 2 is done, we'll drop out, rate will go back to 1, settle will go back to true, and we'll come back down in. If wait time is short, return it. And then we go into the main logic, which says we've got a burn vector. And we're going to look at it. Now, his logic said stop when the burn vector deviated from its original direction. I noticed a problem. If I sample the DT, the delta V vector, not the DT, the delta V for a maneuver node, and it's 90 degrees around the planet from me, by the time I get there, the vector I have is pointing the wrong direction. Oops. So I looked at ways of retaining the initial delta V of the maneuver node snapped just before I turned on my engine, and it got weird. So what I decided to do instead is my termination condition is that the maneuver time remaining is smaller than something. So maneuver time is based on the magnitude of the burn vector and the capabilities of the craft. And if that means I would burn my engine at full throttle for less than some good enough value, which is probably like 1/100th, so 10% throttle for 10th of a second, if my delta V is small enough that I can't control my engine sufficiently to hit it, then lock throttle is 0, lock steering to facing, remove the node, and return. We're done. So then I do this little swizzle here. Now, I actually have done some things to try to move away. We're going to move away from doing all this logic here. Well, we're going to do the logic, but it's centralized. We're centralizing it elsewhere, but the same logic is normal. We take the desired delta t, and we basically discount it by how much we're facing the wrong way. And I'm locking that so that whenever we're going to do this lock throttle, so whenever they evaluate throttle, they're going to call this delegate. Now, by having a delegate here, this means I can do complicated logic in here. I can have if something condition return early. So I could do a bunch of locks here, or I could just do this. This is easier. Anyway, so there is our maneuver code. Coupled along with that, I decided to add another capability, which is to have the maneuver package be able to manage maneuver nodes based on DV. So if I know the DV that I want at a given time, I should be able to, well, let's take a look at schedule. I should be able to create a node that has that delta V. Well, my delta V that I pass in is going to be in the raw ship coordinate frame. And we need to rotate that around because when I create a node, I need radial, normal, and prograde. If you look at it, if we are not flying level, then prograde and radial are not perpendicular. Well, as it turns out, after going through a whole lot of work to try to solve the change of basis into a non-orthogonal basis, it turns out that the radial in this node is not radial. What it is the vector perpendicular to the prograde and the normal that is roughly outbound. So these three lines used to be a lot more complicated. Now they're a lot less complicated, and I don't have to do a matrix inversion. I am so happy. Oh, and also, if that was having to do a matrix inversion, there's a problem of what do you do if you're on a rectilinear orbit? If your prograde vector is exactly radial. Well, the old code blew up. The new code will not be happy, but it won't blow up. I believe what it does is it's going to just ignore the, well, let's see. If my velocity and my position are parallel, let's look at what happens here. We get a P, we get the P direction, which is the velocity normalizer, which is going to point outward. Then we say, what's our normal? Our normal is our velocity cross our position. Well, if these two vectors are parallel, basis n is going to be 0. Oh no! Basis r is going to be a cross product of a 0. So what happens is that if we are exactly, precisely, completely radial, we can't build nodes. So never fly straight up. This is common to every navigation system that at its root does roll, pitch, and yaw, because you pitch to 90 degrees and everything goes wah. And in this case, the major sin that we're doing is assuming that position cross velocity is a vector. It is a vector, it is conserved, it happens to be the 0 vector on a rectilinear orbit. It's not a unique vector. It would literally be any vector perpendicular to your velocity. So we could say that if basis p is equal to 0, we can pick one arbitrarily. We could pick an arbitrary vector as that. Would it be the same vector that the maneuvering system picks? Probably not. So it'd be interesting to find out what happens in the maneuvering system if you are actually rectilinear. I'm betting it doesn't work. Anyway, so you can schedule dv at t. It'll update the node and set it up so you can literally say, here's my delta v at some future time, set a node up for that. And that's going to come in handy because we're doing Lambert solutions now. And there's another copy of it called Update. You can, in fact, merge these to some extent. I messed around back and forth on them. I am thinking that because of some weirdness about what happens when you're trying to predict the position and velocity of your ship, and there's a maneuver node that might be somewhere near, possibly before that. There's some weirdness. The places I do this, I literally am only calling schedule. I'm never calling update, so this may go away. Okay, Lambert. I don't understand the math behind Lambert well enough to explain it. I hardly understand it at all. I cannot explain the solution. I can explain the problem. If I am here in space at a given point at a given time, and I want to be here in space at a different given point at a different given time, and I know my position is relative to the body, and I know the field strength, it turns out that there are two unique trajectories that will get you from one to the other. One's the short way, one's the long way, arbitrarily. And a Lambert problem is to work out the orbit that gets from one to the other. And the Lambert solution, once you plug in the positions and the elapsed time and mu, gets you the velocity you have at each end. So it gets you your starting velocity and your ending velocity. So if I'm here and I want to be there, I can do a Lambert check, and then I could take the starting velocity and subtract out my current velocity, and that's my initial burn. Wow, we have in one step evaluated what do I need to do right now, what burn do I need to do right now to end up over there at that time. So there's our rendezvous. Wow, that simplifies things. We used to do a whole bunch of iterations. Well, it turns out that under the covers inside Lambert, it's doing some iterations. So all we have done is we've hidden the iterative process away from us. But as it turns out, these guys are clever. The iteration it's doing, they create a variable called x, and they make everything in terms of x. And our solution is in terms of x, our problem is in terms of x, and they have an iterative, you iteratively solve for the correct value of x, and then you calculate the rest of it from x. And we don't actually name x here, but that's the Lancaster-Blanchard variable. We are now getting into territory that I have not looked at in detail. I have not yet attempted to follow the math on how this works, because frankly I was doing other math things which I had in my head. I have documented, by the way, the vis viva derivation in my project in a way that I believe is easy enough to follow and understand. So that's real fundamental, real easy stuff. I figure if I can get a decent description of vis viva and the rocket equation and a couple of the fundamental things locked down so they're understood and intuitive, then I can come back and look at things like the Lambert problem and have a stronger basis for understanding it. But I look at this code and I'm thinking, this is fairly straightforward. So the only thing that is going to be the time cost is going to be the iterative root finder. So x is the iterative root finder of lambda. So given lambda and t, for some lambda and t which we calculated up here somehow, we solve for x. And then using X, we can then regenerate all of this stuff, and we get V1, V2 at the end. That's really great. And I am going to close this file because this is hard stuff. I have a copy of this PDF. I have placed it in the project. I'm going to read it over and over and over again. The name is Dario Izzo is the guy who published it. The place I got this code, ManEatingApe, produced something called RSVP, Rendezvous S'il vous plaît. Great package. I don't want to look at it too much because it duplicates a lot of what I want to work out for myself. I do want, my fun here is to work out how to make these things happen. And I hit Lambert. I'm sorry. This is too deep for me. Someday I will start from scratch and build my own Lambert solver. Not today. Anyway, so thanks to ManEatingApe for this stuff. ManEatingApe wrote Izio, I-Z-Z-I-O at one point, and I have corrected that. If you try to Google for Dario, Izio, and Lambert, it might or might not find it. But if you Google for Izzo and Lambert and so on, eventually you can find things. I was able to find many references that were all dead links. I didn't find this link. ManEatingApe found it. I now have a copy of it. Thank you, sir. I have been reading the paper, and it is fascinating. So what do you use Lambert for? Well, typically, what you do is you say, I am in an orbit here, and I want to be in that orbit there. I want a really efficient transfer. So what you do is you say, look at my positions at a number of times in the future, and for each one of those positions, consider transit times, times of flight. So if you want to go from Earth to Mars, you say, well, let's start on Tuesday, and let's check every day to see how much energy, how efficiently could we get from Earth to Mars if we start that day. And then you say, well, where is Mars? And you say, well, how long do I want to take to get there? So you could say, well, for transit times between the minimum and the maximum, let's look at a bunch of them. Let's find the one, let's find each one and look at the Lambert solution, which we can calculate quickly. Then we could say, well, how much delta V do we need? And in fact, if we want to be clever, we say how much delta V at this end to get onto the orbit and at that end to get off of it. And you take all of them and you can make a nice pork chop plot that says how much energy is it going to take for us to get from here to there. And then you look at that and you say, well, where is that minimized? Well, this is a minimization problem. This is an optimization problem. And you can do it with hill climbing. You can do it with gradient descent. You can do it with one axis at a time, finding it. But the key thing is you start off by having a fast way of getting the solution to the Lambert problem, V1 and V2. So where are we going to use this? Well, let's take a look at our first usage of it. I think it's RDV. No, it's Lam. That's right. So I normally would make a larger Lambda package that has all of this stuff, but I didn't want to mess with Lambert itself. So Lam is my package that says three things. First of all, given T1, T2 in the current gravitational, well, I should have added mu as an optional parameter here. Calculate the time of flight, calculate the V1 and the V2 for the ship at T1. So project our orbit forward until we get to T1. That's our starting position. And then take our target at T2, and that's our ending position. Okay. Do the Lambert solution between those 2 points. Grab the velocity of us and the velocity of them and calculate the dV. So this is my next wrapper around Lambert, which says not just give me V1, V2, but give me the actual total dV I want. Boom. And we're going to memorize this. This is the first thing I memoized because this is going to get called a bunch of times. It'll probably get called several times in a row with the same T1, T2, and it calls Lambert, so it's kind of expensive. Lambert takes anywhere from 10 to 100 milliseconds, sometimes 200 milliseconds to run. So minimizing the calls to Lambert is a good thing. I'm looking at how to memorize calls better. We don't have a var args mechanism in KSP or KOS, so it would be a memorizer for one argument, a memorizer for two arguments, memorizer for three arguments, and so on. Anyway, you almost want to say you can only memorize functions who take one parameter, which is an optional list, or a lex. That's the other thing you could do, is you can make your parameter lists all lexicons. You package them up as named arguments. Anyway, so design issues aside. Boom, orbital normal. The other thing I'm doing is, normally you have to call Lambert twice, once for the long way around, once for the short way around. And I found that if I look at my orbital normal vector, and okay, if I look at my, there's the other thing. This is a surprise that I actually have posted to Reddit. If I'm going from Earth to Mars and I take a Lambert solution, it's going to ignore my current velocity. Lambert just takes positions, right? So what if I'm not in the same orbital plane? Lambert can choose a solution that literally does a polar orbit from Earth to Mars, which means a 90-degree plane change at each end. That's expensive. So what I'm saying here is that if the R1, the angle between the two radius vectors, if it's more than 90 degrees, I have modified this function so that we exclude the plane change. So I'm going to take my target position, I'm going to project it back onto my orbital plane. So if we're trying to go more than 90 degrees, we're going to change our target to be wherever he is in my orbital plane. So we're not going to attempt to do a 90-degree plane change just because we can come really, really close. We are off by 1 degree of inclination on a 180-degree transfer. So that's ONV. That's what I'm doing here. So R1, R2, mu, correcting R2 for inclination changes across 180 degrees. R1, R2 fac is the other one. So basically we take the cross product of the two radius vectors and we compare that with the normal vector. So R1, R2 fac is going to be greater than 0 if we want to go the other way around. So what this does is it says if the phase angle, if they're ahead of us a little bit, we want to go forward the short way. Get to 180 degrees, go beyond 180 degrees. We don't want to go the short way, which would be reverse. That would be a retrograde orbit. It would be immediate 180 degree phase change. So instead, we say if R1, R2 fac is positive, okay, which turns out that this product, ONV dot R1 cross R2, this will be negative if it's a angle in front of us, less than 180 degrees in front of us, okay? This works even if you're, I don't know, eccentric orbits, yada yada. So this will send in true if we want to go the long way. So long way is forward. Now I actually had to modify Lambert. The original Lambert that comes from RSVP goes the long way basically on this same calculation, but it uses the y-axis of the coordinate system here instead of my orbital normal vector, which means that if I am in an inclined orbit, it would choose the long way, not exactly always the correct direction, but this chooses it in the correct direction. So I wiped out its logic. It still has a flip here, so we can still request the long way here, and this works. That's that one. So now we have, how are we doing this? Oh boy, this wraps back into my unidirectional hill climber. Boy, this could be a 10-hour stream just covering this stuff. Can I maybe do it in Lambda core without getting too much in the weeds? No, this still does a scan. Okay. Without getting too much in the weeds, I have a hill climber that's unidirectional. So we start, instead of having a bidirectional grid where you look at all of your neighbors and you choose the best one, here what I'm doing is I'm saying I have a series of values going forward. I sample here, and I'm going to sample at t+1, I'm going to sample at t+2, and I'm going to continue to increment until I have seen a local maximum. So I'm going to continue to move forward until I see low, high, low. Okay. And then I'm going to reduce my grid size and start at this left one again and go forward to a smaller grid until again I see low, high, low. So each time I do this, I'm always moving. So whatever the starting point is, I'm never going to move to the left of it. This is great if you're doing things like start at time plus 5 minutes. You never want to come closer to your current time, so you just keep moving. So low, high, low, smaller and smaller and smaller, and it will end when we have converged on a local maximum. And the caller can then say, well, I have a local maximum. Let's continue scanning for another local maximum, and another, and another, and another. So the caller can repeatedly do this to get more, but the actual scanner just finds the first local maximum that it recognizes. Now, if there's enough jitter, it may step entirely over some local maximums that are not global. That's okay. We're looking for a series of local maxima, some of the local maxima of the thing, that should include the global maximum. In this case, here is the evaluation function. So the scanner needs to call me back, and its first lambda here is, given this state vector, evaluate the state vector to find the score for it. This is a fitness function for a hill climbing mechanism. So what are we doing here? We're going to do a Lambert. This is in a orbital correction thing. So I have already planned a rendezvous, and I'm on my way to rendezvous. And I know exactly T2. I know the time at which I'm going to rendezvous, and I know the position of the target at the rendezvous, and that's constant, and that's not going to change. What is changing is T1. At some point between here and there, I am going to make a course correction. And I need to know at what point that course correction is best. So where is the most efficient place to make that? So if I'm doing a plane change, it might be immediately, it might be later, it might be halfway in between, it might be half the distance or half the time. These are all things that are difficult to work out, but you can do a hill climber to find the one. So we've got a T1 which we are trying. So the state represents the state you are trying to evaluate. So we pick up T1, we compute time of flight, and we call Lambert. I'm actually going to call Lambert twice here. For this particular thing, this is a final rendezvous for a rescue. It's actually not quite final. It's the final orbital correction. Once we get close to it, we're going to use our engines to try to get within 10 meters. This turns out to be real close. I was delivering us within 20 meters with it. We call Lambert for long way and short way in case it's 180 degrees out. And we pick whichever solution has the smallest delta V at this end. We're not checking the delta V at the other end. Okay. I just got a message from a friend. So that's all we do. We do the score, evaluate the lambdas. This gives us back a score based on how much we have to burn to do it. And the rest of this is fluff for using the scanner, which I'm not going to go into because this is already a lot longer than I wanted to go without doing a launch. I've got to do launches. And we run our scanner to find the first local maximum. It's all we need. For this particular one, in practice, I could go longer. There's actually, some other things I do where I have to go longer. But for this one, I run the plan correction scanner step until it is done. I'm doing all of this in a single call to plan core, so we're not letting anything advance until we have found this. It doesn't iterate, but a couple dozen times at the most. And if we found it, then we schedule maneuver and return. And then it's up to the caller to say, I like that maneuver node, I'm going to go execute it, or that maneuver node is bull, I'm going to cancel it. So there's our rendezvous. We have similar logic, which I am not going to go over for planning the initial transfer. So we are in a 320 kilometer orbit, and we want to go rescue a guy in an 80 kilometer orbit. And basically it's the same thing. Just look forward along my orbit and evaluate at each point transfer to his orbit, and I need to evaluate for various times of flight. And we're going to do one scanner to find the best TOF for each starting time, and then we're going to roll times forward until we find a global maximum, and then we're going to do it. So with that said, as long as we're looking at the rendezvous, let's go do a rescue mission. Let's actually launch this sucker. Let's get rid of the code. So we have one rescue mission. Actually, I was accepting contracts for tourists, and one of my tourists that I wanted to do was, well, I misclicked, and I now have a tourist who's up in orbit that I need to go rescue. He's actually a rescue mission from the contracts, but you're looking for people who want to ride. He says, I need a ride, but you got to come pick me up. So open this up, and we have a rescue, and we're going to use R01. These are actually the same rescue rockets from save 2. This is save number 3. I actually started over from scratch so I could exercise parts of the system as I brought it up. So we haven't rescued anybody yet. This is our first rescue in this save. We're using the vessels from the prior save. So R01, look at R01. This is the nice smaller version of the rescue ship. Let's make sure that we only have one crew, and I'm going to send Valentina up to do the rescue. So this is the ship that has fuel tank, so it's got FLT 400 and 200, so it's 3 tons of fuel, and the Terrier, so this has got a lot of on-orbit Delta V. Turns out a lot isn't a lot. It's not enough to go out and rescue people very far out, as we found out in Save 2, which is why I've got a bigger one. And we've got decent fuel in this stage, and we've got some things, and let's go launch it. Now the other thing I've done is I actually have set up PuTTY. Where did PuTTY go? Let me get a PuTTY going here. Yeah, it's not going to show on the screen, but at least I will be able to monitor what's going on. I'm not streaming the debug console. I haven't got that set up. So please select target. Now, the other thing I've done is I've added Kerbal Engineer, just for other reasons. I just want to make it easy. Slow ships. I'm going to target Dorfrey's pod just from here. Okay. So the thing about this automation stuff I've been doing is that once I hit the button to send Valentina on the way, and I've got got Dorothy targeted, I basically just sit back and watch what's going on here. I don't have to fly this manually, which is really great because if you're going to be, rescuing 20 Kerbals, flying the same problem 20 times, 20 times getting into orbit, and 20 times making the transition, 20 times trying to, yeah, that's all. Doing it manually the first few times was enough. So, the first thing was we now select our initial orbit based on the relative period between the target's orbit and our candidate's orbit. So we find a good candidate where the phase angle repeats fairly quickly, so we don't have to go searching over the next 2 weeks. And in this case, it chose the 320 kilometer orbit. Because Dorothy is down at 80 kilometers. Actually, he's between 80 kilometer periapsis and 90 kilometer apoapsis. So he's not circular. So we got the maneuver node, and now we time warp to get to the maneuver node. And we execute the maneuver node. Oh, what you did notice was that getting that maneuver node, that was using a Lambert solution. It took about 10 seconds. And this lambda correction took about 1 second or less. These are very fast because Lambert is almost closed form. It's a very, very efficient iteration on that variable. So we are now on our final approach. Kerbal Flight Engineer says that, well, it doesn't tell us, but MechJeb says our closest approach distance is 6 meters. So the automated mechanisms have delivered us on an orbit that's going to be 6 meters from our target, which means we are probably going to hit it with the backwash from our engines as we close. This part of the rescue script, this came over with very little changes from the previous save. I did this mostly. In fact, most of the code just came over. I just continued development on it, bringing in packages as necessary. I had to refactor to get them to fit into the new mechanisms, and I had to adjust some names where we used things that were built-ins, and I had to set LAZYGLOBALS up, and I had to use local declarations instead of set, where I was setting something that I didn't have declared local. Yay, fixed that. Okay, so our closest approach was actually within 6 meters, but when we actually synchronized, we were 100 meters away. That's cool. That meant we didn't backwash it right away. And now we do our fine approach. And we are now 7 meters away. Get us nailed down. It's doing all this with the main engine. We don't have RCS here. So I will eventually update this script to use RCS if it has it, and I will have to worry about how I'm going to get RCS to thrust me in the right direction and so on. Okay, so we switch over to this guy, and this has to be manual because, oh, in my test run, I rescued Dorothy. So here is where I would normally take Dorothy out of the capsule and bring him aboard, but he's already been rescued, so I need to remember to get rid of this, and we're going to head back. In fact, I think instead of, well, no, let's eat the cost of this. I've got plenty of funds. I have been doing a lot of tourism, so we're up to 500,000 funds. We need a lot more. We like 1.6 million to finish up our science center upgrades, and yeah, so we're still going to need to grind out some more funds, and we're going to need to get some science from around MUN and so on. Same as the other save actually. But now it's time to go home. So I click on abort. Oh, with the correct one selected, I click on abort. And the rest of this is unmodified from the previous save. So while this is landing, I am going to go refill my coffee mug. I will be right back. Okay, I'm back. And we are still floating down, auto landing. Totally automated from here on. And this rocket doesn't have any Kraken parts. So this particular one always makes me nervous. I always wonder how many of the fins are going to burn off. And maybe I should actually just burn the rest of my fuel while I'm on orbit and just let myself float down. I don't know. I like the theory about decelerating lower in the gravity well, but decelerating sooner, well, the later I decelerate, the more the atmosphere decelerates me. Because the faster you're going, the more deceleration you get out of the atmosphere. So I guess the thing to do is to balance it so that things just don't quite burn off, which is kind of where I'm at right now. It ain't broke. It ain't broke. I'm not going to fix it. So the next steps here, I haven't finished bringing everything in. There's still things that are on the old version of Farkos that haven't been ported over to the new one yet. For example, I don't think I have all of my satellite control stuff done yet. So that's going to have to come over. I have done a whole bunch of things that are new. When you saw the list of packages, things like a scanner I went over, which is basically a unidirectional hill climber. Kind of nice. It turns out that if you configure it right, you can almost do a binary search with it. When you can say, well, I'm looking at the next day, so let's step forward by 4 hours at a time. And when you find it, you know it's between A, B, and C, which is A plus 4 plus 4. Well, now you can set your delta down from 4 hours to 1 hour. Now you step forward, so you can do more efficient searches. Not quite a binary search. You can do binary if you want by cutting it in half. It'll evaluate some things in extra time. The other thing is, if you're clever, you can memoize more aggressively in your evaluator. So, for instance, if I'm evaluating it at times 0, 4, and 8, and the next time I do it 0, 2, and 4, if I can remember the 4 from before, then the evaluations end up looking a lot like a binary search. So, yeah, so there's that. I'm not sure how many older versions of the result you would need. Yeah, it would be some tinkering. A cache of recent memoized values somewhere. Anyway, so there's that. I'm tending to do more with the delegates than I did before. The obvious things I can mention as being notable. Oh God, the commit that I did that brought all this stuff forward was crazy. Memoizer, matcher, non-volatile storage. Let's talk about that for a second here. So the canonical way to do non-volatile storage in KSP would be to use the JSON mechanisms, so JSON write and JSON read. And I've got a co-pilot who wants to help out with this one. Well, as it turns out, it is not a compact JSON representation of your Kerbal data. So what it is a JSON encoding of the C# objects, which includes a huge amount of repetitive text because it's identifying the C# objects that you're storing and restoring. So that very quickly, what do you want? You wanted to be picked up, and now you don't want to be picked up anymore. Hold on. I could talk while I'm depositing. Maybe she wants under a blanket. So JSON wasn't working for me. The other thing is that most of these formats, if I'm storing a bunch of name-value pairs, I'm storing the names. And I'm storing some indication of the data type because you're going to load a value from non-volatile storage, and it might be a number or a string or a list or a position or a velocity or a body or a target or whatever. Anyway, so there's some encoding there of the type. So you got the type information and you've got the name of the thing. That uses up a lot of storage. We've only got 10 kilobytes. And we only have that 10 kilobytes if we're storing nothing else there. So right now I'm storing the boot script and that's it. Everything else I'm loading from archive. I don't want to store my non-volatile storage to the archive because if you rewind, you're going to get the stuff that's stored from your future. So I want the rewind to rewind the state of my non-volatile storage, which means it has to be on board. Got it. So what I do instead is A0. I am going to take the name of the thing you want to store, and that's going to be the file name. So if you store something under foo_bar_baz, okay, foo/bar/baz is the name of the thing you're storing. It's going to open a file called foo/bar/baz on the local storage and put your value into it. And I needed a very compact way to represent the value. There's no way to like stream out the bytes, so I am using text encodings. So when we collapse the NV package completely, we see that here. So if I have a scalar that I'm storing, then I convert it to a string. If I got a string that I'm storing, I put out a quote mark followed by the string. Vessels and bodies go out like that. Okay. I could have sworn I added booleans to this at one point. Anyway, you can add all sorts of things. I'm looking up in here based on the data type that I'm storing, and that has to be coordinated with NVDEC, which has to be able to recognize the serialized string and regenerate the deserialized content. This will fail if I store a vessel, and when I try to load from NV, the vessel is gone. What will happen is we will crash here, because it'll say, you're trying to load up a vessel called ComSat3, and ComSat3 doesn't exist, so I can't create a vessel called ComSat3. We'll cross that bridge when we come to it. Anyway, so we still support get, has, is, put, and clear. So get the value, ask if non-volatile memory has a value for something, ask if the non-volatile memory contains this exact value, put the value in clear. So clear deletes the file. Does some memoization, talks to the disk when it has to. The ones that take values, I said, well, what if I pass a lambda? Most importantly for get takes a default value. It says, if it isn't stored, if I don't have a value for this, give me this one. So I can say, get my launch azimuth. If it's not set, just hand me back a 90. Well, what if the calculation of that default value is expensive? So if default is a delegate, we can use this eval function, which I've written over in the standard library. It says, eval says, if my parameter is a delegate, call it, return its return value. So now all these functions in non-volatile will take delegates, and if they are handed a delegate, they will evaluate the delegate to get the value. So you can't actually store a delegate to a non-volatile RAM. What you end up storing is the current value of the delegate. I'm good with this because I have no clue how I would store a delegate and restore it later and have it be sensible. What else? Task. I believe I was doing something along the lines of task in the old save. Basically, it drops a GUI element up and you turn it on, and periodically your flight control software says which one of these tasks is enabled on the GUI and matches its condition, and if so, go do it. This is how I did the development platform thing. Hover is a standard hover controller, which I added a lot of comments to, and I tweaked it a little bit. So you can say things like, "I'm at 10,000 feet. Please hover at 10 feet," and have it do something sensible as it comes in, because a linear air controller will attempt to overdrive your engines when you're too far away, and as a result, you'll come in too hot and you'll overshoot. And if you use the equations of motion, then you can do things like, oh, we're so far away, let's use the correct v equals square root of 2ax to pick our velocity, so that whatever acceleration we need, it's that same acceleration all the way down instead of way too much acceleration at any point. Hill climb, go CTRL. Right. Okay. I mentioned this earlier. K0. Basically, I had logic in a lot of places that did the same thing with the throttle. It said, take the delta V that we want and compute an acceleration based on the gain factor and the divided velocity change. Compute the amount of force we need in this ship right now to achieve it. Compute the throttle that is required to achieve that force. And then look at what our facing area is and discount our throttle and then lock to it. So all this logic, this appeared many, many times. Some places it wasn't complete. So now it's here, it's in one place, it's complete. And it takes a DV, which may be a delegate. So you can lock throttle to control throttle to call this function each time, and if you pass in a delegate for DV, it will evaluate the delta V every time. Same thing with steering. If you've got a delta V, evaluate it. If its magnitude is greater than 0, then set our facing to that direction, maintaining our top vector. Now, if our delta V requested is absolutely 0, I am going to go ahead and put us in our idle pose. So if we ever compute a 0 delta V as part of a maneuver, when we hit that, we're going to the idle pose, which may hit the idle pose more often than we did before, but that's okay. That's perfectly okay. And the idle pose is the one we've used before with some changes. So if we're in space, okay, we're nice and clean out in space, nothing around us, then we point our nose in the direction of our angular momentum. If we're in an equatorial orbit, that's going to be up. And we arrange it so that our radial vector is the direction our head's pointing. Okay, good enough. If we're inside the atmosphere, then we want our idle pose to be a little different. If we're going up, if we're ascending through the atmosphere, then I am going to idle pose us as point the nose in surface retrograde. So I'm pointing our nose into the wind as we're ascending. If we're coming down, I'm going to go the other way. I am going to point the nose away from the wind. So we're going to come in tail first, which is where our heat, that should be where our heat shield is. If we've got an engine out there we're going to use to decelerate, that puts the engine in the right position. So this sets us up to decelerate. Now, if our vertical speed, if we're essentially leveled out and not going up or down very fast, and these are probably tight limits, airspeed is greater than 100, then I am going to point us into the wind again. So I considered saying, if we are level, just point us upwards, and I thought, well, what if we're going that away real fast? So if our airspeed is slow, then we get our normal. We're in the atmosphere, we're not ascending, we're not descending, we're not moving sideways real fast, so we're just going to face up. And these together, it means that as we cross these thresholds, we'll yank ourselves from one orientation to another. There's no smooth transition. On the other hand, it works. Generally, I fall into one of the categories. So any code that wants to make use of steering and throttle can call this, and it can set the gain and the angle, minimum, max. If you're within Emin, it doesn't discount the throttle, and if you're outside Emax, then it gives you 0 throttle. And different phases of flight will have different criteria. For instance, if you're in ascent, we want to be full throttle as long as you're not more than like 90 degrees away from where you're pointed. So that's the change to CTRL. Rest of this is all normal stuff. There are probably a great number of things in here that I have not talked about ever. Getter, for instance. This is so short, it's simple enough. You call getter with a delegate, and it returns a delegate. And the delegate in return says, hey, remember the last call to this function and the last value it returned. And okay, so for a getter, remember the last time we called it, the last value. So if time seconds hasn't changed, we're in the same physical tick, and we call a getter, it's going to return the value that it had last time. If it's a different physical tick, we're going to call the getter, which may be expensive, and memoize it. So we're going to extend memo later on to do things like, we're calling a function with a parameter, so memoize it for a value of the parameter, or latest value of the parameter, or several values of the parameter. We'll see about how we're going to do that. As we come up with things we need to memoize, we'll have to tune that. Match, Lambert, IO. Yeah, I don't think we're going to go over any of the rest of this. If there's anything here I haven't covered, these packages tend to be small. Go for it. Ask questions, leave me a note, whatever. Bop me in stream, and I will bring it up and show. If I'm streaming KSP2, I might not want to bring this up. On the other hand, maybe I will. If you're the only person on the stream and you want to talk about this, we can do it. So we didn't actually get a rescue out of this, so let's go take some rescues. Let's take all the rescues. Rescue Nelly, rescue Lubo, rescue Nabby, rescue Grayery, and tourists. Let's not grab any tourists this time. We have a satellite schedule, a couple of satellites, slightly inclined orbit, and a slightly inclined orbit. This one's, I don't think I worked out the logic before for putting a satellite in an orbit where they specified both the longitude of the ascending node and the argument of periapsis. I think the biggest specifics I did were AOP, periapsis inclination, and longitude of the ascending node. Argument of periapsis means you're essentially matching a specific thing in that orbit. And this is most common if you're looking to put something in a kerbosynchronous orbit. Anyway, so we'll face that one when we get to it. So active. We still have some tourists active. We have a bunch of tourists active, and we have a bunch of rescues. So let's go fly a rescue here. Oh, let's take a look. If we've got far rescues, we're going to want to use the larger vessel. So let's see here. Back out to the Space Center tracking station. So do we have somebody that... Oh, look at all of that. Looky there. I'm going to go rescue the far one. So Nellie is going to get rescued. Nellie is at 18 million meters. So 18,000 kilometers. She is far, far away. She is beyond the orbit of Mun, which means my automated mechanism for going and grabbing her, which doesn't care about Mun. If we get an intercept orbit, we are going to have to abort and try again some other time. So Nellie it is. And we're going to need to use the larger of our rescue vessels. So this is R02. Now you notice that instead of having the 3 solid rocket boosters, this has 6 of these guys, each of which have an FLT-800 and FLT-400 and liquid fuel. So that's 6 tons of fuel by 6 of them, plus the guy at the core. And they are in a asparagus staging configuration, which is my favorite kind of configuration. The main core in the middle is generously sized and has RCS units. And we have a re-entry model that can take a pilot and a passenger. Yay! Now let's crew this. And Jebediah and Bill always want to jump in there. And we are going to send up Valentina. So here we go. And I can turn off the code editor. We are targeting, as flight engineer over here has a nice thing. I could go out to the map and chase down Nellie's capsule, or I can just click on it here. And this is our old pad hold code, almost completely unmodified, which is going to pad hold us until we are approximately under her ascending node. Time work complete. Then we're going to get our 10-second countdown. There's some debug stuff that got printed. So earlier today I launched a rocket of similar configuration in KSP2. And initially the fuel danced just like this. But when the first stage dropped, they didn't go back to full. They kept going from where they were. I think that's a display bug in KSP2 because we still got the delta V that we should have gotten if the fuel had been transferred. But the numbers next to the graph looked weird, and the graph looked weird. So I am leery of the fuel display on KSP2 and the fact that it may have a bug when fuel tanks are being refilled during the mission. Okay? So be aware of that. And don't freak out if your asparagus staging looks like it's not working. It does appear to work, because if it wasn't working, I would not have been able to fly where I flew. I have some dinner. So, we are headed out to Nellie. She's in a highly inclined orbit, which means we're pretty unlikely to actually get an encounter with Mun in the process. It also means that because we are naively flying at an azimuth equal to her inclination, and we are still being carried around Kerbin by our or our surface velocity, it means that we are probably going to have a bit of a orbital plane change at some point. It looks like currently that's at 2 degrees. That's not too bad. And I am not sure what my script is going to do with the plane change. I think the plane change is now left to the Lambert correction. But now it's just a matter of watching it and waiting for it to happen. So we are still gliding up through the atmosphere. There we go. We're in coast phase now. And it will have selected a fairly low orbit. It's going to do an 80-kilometer parking orbit to stage and ready. And once it circularizes, it will very quickly do the initial Lambert solution based on what if there's no plane change. This is going to have a big error in it. Because I draw a perpendicular from the target to my plane rather than an arc. So my correction burn is going to be massive. So if we project everybody into our orbit, oh wait a minute, no, it's not going to be massive because we are starting out with a, yeah, so we are not too bad. We're only a few degrees off. So it's only a couple of, if I actually had launched into an equatorial orbit, then it would be a massive change, but that's going to be inefficient any way you cut it because you've got that, what is it, it looks like about a 20 or 30 degree plane change. Okay, so that quickly it planned the Lambert. And we will have a 1.9 degree plane change at some point. Why isn't it? Oh. Okay, we ran out of control authority and didn't get to the right place at the right time to make this burn. So this burn's going to be off a bit. It's a good thing we're going to do a correction burn. Okay, so I am not allowing enough time for this vessel to reorient. So according to KSP, that's not good. So this script is borked. I had a staging event, and the staging event caused us to abort that transfer, and now this is going to try to correct. It's treating this as an orbital correction. It may be our only orbital correction. Yeah. Okay. And I think that the script that I set up does not allow us to come back and do a second orbital correction because, of course, a Lambert correction was going to be great as long as it wasn't too far out. It should have corrected again. Yeah. And yeah, this is no good. I need to rework my logic because this is not going to be a viable rescue. I have a lot of fuel left, probably enough, but this is not the efficient rescue I was looking for. So, okay, so the bug is if I have a staging event during a maneuver, it is terminating the maneuver. Not good. And at this point, I need to look at the debug console. And this says program aborted. So I got into the approach phase, and it aborted because I have no electricity. So there's a second bug. The second bug is that I'm sitting here pointed away from the sun, and none of my solar panels are seeing anything. So we now have a weakness. We absolutely positively need to be in our pose to get the solar panels exposed during that long transit. And secondarily, so there's two bugs. So number one, maneuver nodes have to be able to recover from a staging event. Number two, we absolutely positively need to assure that we are in our pose before we time warp, or we're going to come out of time warp with no electricity. So let's revert flight to vehicle assembly. Now I'm going to pick somebody closer in so we can actually do some sort of a rescue here, because I need to eat my dinner. I'd like to actually see a rescue happen today. So the tracking station, we're going to look at it. I'm thinking, what have we got? There's our ComSat. Let's just do somebody in a real close one. Oh, Dorfrey's pod needs to be dumped. Dorfrey has been handled. So how about Riching? And he's in close, so we can use R01, which is a cheaper craft. So from 33,000 funds down to 20,000 funds. And crewed by... Hey, JetBill, get out of there. Valentina gets to do this one. Oh, wait a minute. Dorfrey's a scientist? I wonder if Dorfrey could... I could send Dorfrey up to do this. Nah, let's send Val. Dum, dum, dum. Okay, so it's going to be Riching's Hulk that we're headed for. Center the view on Kerbin. And I am going to cut the camera while I eat dinner, and we're just going to watch this rescue happen. That was the Lambert planning. This time the correction is halfway. So that was the location at which Lambert gave us a local optimum. So it's a burn of 1.5 meters per second. And if we look here, we notice that we are going to be within 4 meters. If we just coasted, we would swing 4 meters past it. So we're going to end up some distance away because of the way this works. But very, very nice. And hit the abort button to return home. Okay, I am back. And I am revising the maneuver script to do the right thing. We have rescued somebody. And I think at this point I am going to call the end of the script, or end of the stream. Just to give a heads up on what I'm doing, I'm going into the maneuver script, and where it is computing what it should do, the problem was that it was saying good enough based on the remaining time, and if we were staging, that fell to 0. So, part 1 is if we have no available thrust, but if the ship still has some delta V, return early on having made no changes. The second thing I want to do is I want to hook into the new control scheme rather than the partial logic in that particular code for the throttle. I want to hook back into CTRL to control the steering and such. Actually, instead of canceling the stream, I can just do this live on stream, and if people don't want to watch it, they can tune out. So, I'm already part way through. Blink, blink, make this decent sized. So, first part was here. It's easy enough. There is a thing called ship delta V current, which gives the total delta V available on the ship, even from engines that are not yet ignited. This is per documentation. So you should ask for ship delta V, it's the hole on the ship. You can also ask for it on stage. So as you can say delta V in a stage, but this one we just want to know if we currently don't have any thrust, but there's still some on the ship, then we're going to return and say call us back in 1/10 of a second so we can reevaluate this, because we're clearly supposed to be making a decision. And we're going to do that early. I am going to do it right up at the top. We're making all these other decisions. We're saying if abort is turned on, then we're done. And if we don't have a node, then we're done. And if we're time warping, call us back in a second. And if we are coming out of time warp, call us back in a second. The idea is if you're time warping, you're probably not within a second of something interesting. Then we're going to say if we don't have no thrust, but we still have delta V, call us back, but really quickly, because staging is fairly quick, and once the staging is done and the next engine is ignited, we want to jump right on it. Okay. Next thing is we want to make use of our steering. In fact, I'm going to just, from here on down, I'm going to do all new code. Old code. What we want to do is something like this. So now a DV needs to be a delegate. So local DV is, and we don't want it to be evaluated multiple times in a given tick, so we're going to use memo:getter of a block of code. Now, inside this block of code, we're going to compute and return the DV that we want to currently use. Now we are going to need to do some things to determine if we are done. We're going to return a 0 DV here. Okay, 0 DV will put us in the pose. How about that? Okay. So identically returning 0 from DV says we are done, go pose. On the other end, we're going to have to do a delay to make sure we get into our pose before we warp, yada, yada, yada. What other conditions do we want? Probably nothing else. And if DT is good enough. So the other thing is we're going to need to decide, if we're good enough, we're going to go to 0 as well. And I started pulling the logic together here, and that's yick. So this is all based on DT. I've taken care of that. So we know what the burn we want is. It's there in next node. this is going to be evaluated over and over and over again, so we are not protected. So we're going to start off the top. If not has node, return the empty. Return, yeah. If there's no more node, we're done. Okay, so we grab the node. We grab our burn vector. This is actually the value we will return if everything is good. So under what circumstances do we not want to return the burn vector? Well, okay. Obviously, if it's not time yet. So let's pull this stuff up. If it's not time yet, we're going to return 0. Hold on. So we've got two different things to return 0 for. We've got a return 0 saying it's not time yet, and a return 0 saying we're done. So I do want to set this lock up, but I don't want to be starting to look at dv equal to 0 until we are after this. So what I'm going to do is I am going to watch NETA, and if NETA is negative, I'm not going to return. So we're going to modify our check for completion. So we're going to check for dv0, and we're after, and ETA is negative. I'm hoping that's right. So now we look at this. If wait time is ETA minus maneuver time of, call it BV, so burn vector. In fact, let's use burn vector. It doesn't really matter. There we go. So BV is burn vector. Wait time is ETA minus half the time to do the burn vector divided by 2. Maneuver time should be fairly quick. Okay. If it's not fairly quick, we need to fix burn time. It may very well be that there's some things in burn time that we can deal with. The fact that we're using memo here means we're only going to call this once per phys tick. We're cool. Start time is seconds plus wait time. So now if time, more to the point, if we haven't reached start time yet, then wait time is, if wait time is greater than 0, return that. So if we need to wait, don't burn. That will put us in our idle pose. That's not good. I'm beginning to think that we don't want this DV to be struck yet. Can I manipulate the idle pose? So inside MNV, well, we're inside MNV. This is inside CTRL. What I want to do is intercept pose here and have pose return what we want. Okay. Or I could set dv mag to something so incredibly small that would work. So I'm going to set my dv, if I'm before the thing, I'm going to set it to a non-zero value, which doesn't have any viable thrust. So inside maneuver, we're not going to return 0. We're going to return bv times 0, bv divided by 1,000,000. So itty bitty teeny vector, pointed the right direction, but itty bitty teeny vector. So non-zero. So this solves both of those problems. Now, do we need start time? I'm not sure we need start time. So we only get past there if we are at or after start time. So we don't need to calculate start time. We do need to calculate it outside, though, because we are going to do a warp 2. So we still need to do these outside in support of warp 2. And that means I need to have these things. So next node we've already checked. There. Okay. Now we can check those first. Now let's. So given that the node isn't going to change, I don't actually need to fetch node here. What if the node goes away? Now, if the node goes away, then I would no longer have a node. We return 0. So if somebody deletes n, if next node not equal to n, return. So if somebody deletes our node and there's another node there, we're going to return 0. I'm hoping we can compare nodes like that. Okay, so if there's 3 nodes stacked up and we're doing one and somebody kills it, then instead of starting to try to manipulate the second node in line, we'll just do this. Fine. Okay, we'll just return 0. I'm assuming we can compare nodes. If we can't compare nodes, this is going to fail. Pick up the burn vector, calculate wait time, and decide to do a nearly 0 burn. Okay. Next node, and we need the burn vector here. We could probably initialize burn vector up above. We need to reload it here, so it doesn't matter. Now let's defer it until we need it. Yagni principle. You ain't gonna need it yet. So now we say burn vector is that. We calculate wait time. We calculate start time. Our steering is already handled. So now we say, if we have more than 60 seconds to wait, well, we're already. So I was doing something weird. I was actually setting throttle, and under KSP, KOS 1.4, you do not set throttle, because throttle is a global lock, and if you set something that's a global lock, that's a conflict with an existing built-in. So you always lock. But that means that we're not going to do this if throttle greater than 0, doing something weird. This just says if we're waiting more than 60 seconds, and we're going to warp to 10 seconds before start time, this was not far enough. I'm going to give myself 15 seconds to slew. Let's give ourselves 20 seconds to get our attitude set. We're going to warp to that. Okay, so that's if it's greater than a minute. Otherwise, if it's greater than 0, then we return a time to wait, which is 1 second if wait time is bigger than a second. So we'll come back in a second. If less than a second, we're going to wait shorter periods of time. So now we get down to here, and we're going to evaluate dt, which is the maneuver time for the burn vector. And we're going to say if it's good enough. But what happens if we are out of thrust? Well, if we're out of thrust, we already handled it. So we already know that we have thrust. So now we look at maneuver time, but we're not going to do that. We're going to base this on if dv returns 0, which means this good enough logic goes in our dv getter. So now we're going to say if dv mag equals 0, then we're good enough. And in this case, what we're going to do is we're going to lock steering to to CTRL of steering. Okay, and throttle. So we're going to lock steering and throttle to the idle, and remove next node. So remove n. So remove our node. Now, if somebody else removes our node in the middle of this, then we're in trouble. So we're going to say if has node and next node equals n, then remove Um, Finding out if a node is scheduled. There is no node colon n colon scheduled, which would come in handy. This just says if we're currently working on node n still, we're done. Now I want a delay to get it to allow us to slew back into our idle position. So I do -10 as my return value, which says wait 10 seconds before calling the next step in the mission plan. And that takes care of the termination condition. Now, if dvmag was not 0, then we have already locked our steering and throttle appropriately, and here's the return 1. So that should be good. Now we discovered this doing that rescue of that FAR guy. So let's repeat that particular mission. And get this guy off the screen. No doubt there's going to be syntax errors galore. Okay, back to this. We have rescue R02, and we know that our staging is such that we are going to be discarding the last of our long pencil on our way out to who was it that we were going to rescue? I forgot who it was. It was this guy that's way far out. Nelly. Yes, Nelly's capsule. Nelly, who has a whole bunch of... She's connected to our network. Yay, ComNet visualization. I suspect that I have our ComNet set to always connected, and that's... I'm going to fix that at some point once I start putting up ComSats. We'll turn that off, so we'll have to maintain communication. So Nelly is the far one. She is out there at distance 19 million meters. Let's go see if we can rescue her, including the staging event that happens while we are trying to match orbits with her. Why have I got leftover debris from a T-30's launch? Fine. So, Nelly. Okay, who have we got crewing this thing? Bill and Jeb, get out of the seats. Valentina, you're up. Okay, we're ready to go. I have my debug console running, and it is waiting for a target. So we find Nelly's capsule and target it. There we go. Waiting for her ascending node. So the volumetric clouds are from an add-on. Not fair to say that KSP2, ooh, it doesn't have volumetric clouds. Well, of course not. Neither does KSP1 unless you load up a whole bunch of mods. But even so, I am liking the KSP2 stuff, by the way. I will be doing a lot more KSP2, especially as they start adding features, things like career mode, science mode. Multiplayer is going to be a big, massive thing. I have friends that play KSP. Yay! Interstellar when we get there, colonies when we get there, all sorts of things. But for now, it's a sandbox where you can launch rockets and do interesting things that are fun. Had a heck of a good time today. Did a manned flyby of Mun. I got myself in orbit around Mun and got myself back out and wound up back at Kerbin with a huge amount of Delta V available because I overbuilt the vessel. I basically used the same configuration that we're flying right now. Not as much fuel, but there's still the 7 engines down at the base with the fuel ducts. So asparagus is the win. Anyway, a lot of fun. There are some interesting improvements in KSP2. For instance, when I go to the map and I go look at Mun, it will show me its sphere of influence, which is fairly large. It's like this big. So yeah, and when you're setting up a transfer orbit and you're looking to make it match, you can see where it's going to touch the sphere of influence. So very nice. Okay, so that sound in the background is us using our RCS to get in the correct orientation. I suspected that we crossed over into space, so it was immediately going to our idle, and Ascent took back over to drop us into our preparing for circularization. So all that noise was wasted RCS. Oh yeah, in case you've forgotten, these missions now have a background task that turns on RCS based on your current steering needs. So if you are facing a long way away from your steering, or if you are rotating rapidly, it will turn the RCS on, and then when you get to where you're faced basically in the right direction and not rotating rapidly, it will turn it back off again. So we don't end up jiggling the RCS when we're in that dead area. We just use our reaction wheels to keep us properly aligned. See there, we're firing RCS to get us to turn around to the idle area. It's doing Lambert planning now, and it failed. So let's bring up this, and I can show the debug console on the screen. Hold on. Okay, so there's actually a bunch of debug output from the Lambert planner. It's looking at various T1s and what the T2 scan returned, but now we've got this undefined variable name memo because I forgot to import the memo package. So local memo is import of memo. And yeah, we are going to have to rewind this at some point. what was the next one? CTRL was also not imported. There. Now if I try to continue running from here, it might work. See if I get that to reboot really quick. There we go. Phase lam xfer. Okay. Yeah, it's trying to do the Lambert planning of the transfer now. Yeah, this is... Oh, right. The phase labeled lam xfer applies to both the planning and the maneuver node execution. So there we go. Next thing is on maneuver line 100. This is another line I modified. I return B. I should have returned BV for burn vector. And we're going to let it try again. And we should be staging soon. As our DB is going down. And we continue burning after the stage. Yes! Bug fixed. I don't know if we're going to be able to have a successful mission or not, but I successfully solved the bug. So Lambert, and notice that we are out by something normal to our old plane vector, or normal to our old plane, or orbital plane. And now we're trying to go to the idle this is chasing the burn vector. So my logic for terminating a maneuver node is now broken. So notice that our burn vector is 0.0 meters per second, burn time 0.1 seconds. And it is all over the map. So we go back to here. Let me turn on the code editor. And this is the termination stuff. The original code that Cheers Kevin used would save the initial burn vector and would stop when your current burn vector dot product the original burn vector was negative. So when you basically, it didn't runtime correct it. Instead, we have swapped that for swinging around like insane. So what I forgot to do is I forgot to put the termination logic in here. So notice in here I forgot to say if BV is tiny, we are done. So the logic for that is if MNB time of BV mag, well, we calculated that up above. Local DT is MN is this value here. Okay, so we've got the burn time. I'll call it BT for burn time. So first of all, if we're before the wait time, we're done. Now, if BT is less than good enough, return V000. There's our termination. So that V000 says we're terminating if we don't have a node, or if it's a different node, or if our burn time is smaller than 1/10 of a second. Okay. Well, smaller than good enough. I need to look at the Git stuff. Where is fork? I have a utility for dealing with get stuff. And our old condition was verifying less than, if dt was less than or equal to good enough, then return. And we had a value called good enough. And good enough came from where? It comes from here. So it was configured at the top of step from MNV step good enough. And this says within 0.01. So this would be 10% throttle for a tenth of a second would be the smallest burn that we want to do. And that has been good enough in the past. So now if we were to reboot, I think it would pick up and notice that we are done. Yep. And that verifies that when we are done, we are shifting back over to our pose. So at this point, we should be getting some electricity flowing in. And indeed, our electric charge is still topped up, even though we are warping a long way. Okay, and we started our lambda correction. So why is our correction stopped? There we are. It wasn't time for it yet. Okay, so back to idle. And that corrected us. And now we have a closest approach distance of 6 kilometers. Kind of long, but for a far out orbit like that, I'm willing to accept it. We will cruise in from long distance. There's going to be an error introduced by the method we use for synchronization at the end. We have to do a big burn to correct our velocity anyway. It's going to introduce a large positional error. So getting closer than that 6 kilometer value. Oh, yeah, 6 kilometers. Yeah, not a big priority for me. So what we're going to do is we are treating this as a falling problem, a stopping time problem, where we draw a plane which is perpendicular to our direction of travel, which is just to this side of the thing we are synchronizing with, and we do essentially a suicide burn to stop at that plane, which would put us just before the target if we were online with it. We're not online with it. We will never be online with it because of the way the geometry works, but it still puts us close, and it puts us at a low velocity. So low velocity and not too far distance. And now we can go into just a normal, pretend we're in flat space and do a normal controller. We don't have to worry about the fact that we're in a rotating reference frame. So basically we point at it and we accelerate until we're heading towards it at some velocity. And we spin around. And this is going to flicker it around a bit. What we're doing is we're trying to maintain a velocity coming in where the velocity is it's calculated based on our distance. And I think what's happened is that I've done something where something isn't locked, where I'm getting stepwise changes in our target velocity rather than having it all be smooth. So I will be reviewing that code. This is the rescue phase of the mission, which is the fine control. So we're doing a couple things here. First of all, We're having to pulse the engine because we're getting sudden changes in velocity target. And we are having to use our RCS because our changes, our errors are moving around. Still, this is smoother than I could fly it by hand. But I would rather see a constant low throttle than this blipping. In particular, I'd rather do this entire approach on RCS. Well, do the major approach by coming in, at 10% or 20% throttle, landing at 100 meters, and then come in RCS. But this is good enough. Notice we're sitting here under 10 meters, and we're back in our pose, and our electric charge is staying topped up, which is what we needed. Okay. Now the pose is perpendicular to our orbital plane, which we notice it's tilted on its side because our orbital plane is highly inclined. And now we can go have Nellie make the transfer. Okay, Nellie, step off into space. And I wish I could autopilot this part, because I am no good at maneuvering with a spacesuit. Board. Oh, grab. I want to do is board, but there we go. Okay, so there's Nellie, and now we just need to deliver Nellie back to ground. Ba-ba-dum. I can turn off the debug console and hit abort. Okay, so coming in from this far away, lowering our periapsis down underground is probably not our best approach. Oh, I left my code editor up on the screen. Doop. Doop doop. So, yeah, this is going to come in really hot. This is something where I may want to adjust my deorbit script to know that we only need to deorbit until our periapsis is just barely in the atmosphere, and maybe have some smarts there based on how high how far we're coming in from. So we are warping at 100x. Which is nowhere near fast enough. So I am going to step all the way up to here. Okay. So I also have a mod loaded that is automatically grabbing some science for me, because that got to be a bit of a chore. Notice in very large orbits, this is doing piecewise lines on them. Okay, and we are overheating like crazy. So there's that. Yeah, that's kind of a hectic ride. If we're there, we're safe, but it'd be nice if we didn't have such an exciting re-entry that burned up so many parts. Let's take a look. What did we get? We lost our landing struts. We lost our RCS jets. We lost our liquid fuel engine and our tank and our Sepratron. And, oh no, we separated, okay. And the monopropellant tank collided into the reentry module, which fortunately didn't destroy the reentry module. So yeah, we're going to want to adjust the script that does our reentry, which is in phase. So that's phase. Should be a descent phase. No, where did it go? Where did it go? Deorbit. Deorbit. So deorbit should say, don't really lower us to 0. What is it currently doing? So here's deorbit. So if periapsis is, so it's saying I'm picking a height which is 75% of the atmosphere. So that's going to be 70 times 0.75 is, yeah, anyway, 80 would be 60, so 70 is going to be 55-ish, I don't know, something like that. If periapsis is less than the height, then we're done. We turn off warp. That's left over from other code. Okay. We are calculating the desired speed based on vis viva of our current altitude on an orbit that ends up at H and is at our current apoapsis. Okay. So we're setting our current, we're saying here's our desired speed, and we're working out the speed change, and we're thrusting retrograde based on the desired speed change. So this should gently bring our altitude to that target, but it way overshot. So what that tells me is that the gain is too high. We need to plan on lower throttle per acceleration. And when we're farther out, a smaller amount of acceleration has a larger effect on our periapsis. Now this is a good script for close in. We may need to, I will have to think on this. I can't do this on the fly. So we'll just accept the fact that coming in farther away, we're going to come in hotter. So, we actually picked up some science. Apparently, we hadn't yet captured EVA for while in space high over Kerbal. So, in the process of doing the rescue, we picked up that EVA. EVA report, EVA science report. What's the difference between EVA report and EVA science report? I'm wondering if the add-on that I've got triggered a experiment it shouldn't have. Okay, anyway, we got 12 science for the EVA report, 37.5 for the science report, bringing us up to almost 200. So we can open up 2 of the science research areas that are worth 90 next time we need it. We have a big chunk of funds. We've got a great reputation. We have a whole bunch of Kerbals that need rescue. We've got a bunch of tourists that need to go, and we need to build up money because, well, he's fully upgraded. Most of these are actually doing okay. We haven't yet upgraded the spaceplane hangar. And we need to pump 1.6 million into the R&D to be able to finish, to be able to do science that is higher than 500. That's going to be a while. So we don't need that 1.6 million until we're trying to do out to this level. So we can get all of the science at this column and this column and this column. These next three columns are all doable on our current expansion. So we don't need the 1.6 million. But that's something I can just kind of putter around with while I debug code and let it do another rescue and find more bugs, and let it do another rescue and find more bugs, and so on. Not something I want to stream. It's just iterative, find, fix, but there you are. And I'm going to call this a stream because this 1 hour stream turned into 2.5 hours. So I will see you when I see you.